All right, let's take a look at our last related rate problem, the sliding ladder. We have a 13-foot ladder and it's leaning against a house when its base starts to slide away. So right over here, I've just gotten started with a little right triangle here. We're going to call this our house. We're going to call this the ground. And this would be our ladder right here, our ladder that's leaning up against the house. So we form a right triangle. And it tells us that the base is slipping away. So I'm just going to put an arrow here to indicate direction. All right. So it says by the time the base is 12 feet from the house, so we're talking about this distance right here, the base being 12 feet. So until it is 12 feet away, we're just going to label it as X. That's the horizontal component. All right, by the time the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. So I'm in the decoding stages and labeling. All right, so I don't know what this is, but I do know that when the base is 12 feet, it's moving at a rate of dx dt is 5 feet per second. So I want to pay attention to a positive negative sign. It is going to be positive because my direction is to the right. So the rate of change of x is 5 feet per second. Okay. Let me also label the ladder, the hypotenuse, as 13 feet. Okay. All right, so that's some given information that we have here. I'm paying attention to also the vertical component here. We do know that throughout time that as that ladder is sliding down, or the base is moving this way, that the vertical component is decreasing. It looks like the horizontal component is increasing. Maybe when it was flush up against the wall, our distance was 0, but then as we start to pull it away, x is increasing. Of course, it wouldn't be any larger than 13 feet because that's the full length of the ladder. Okay, so x increases and y decreases as that ladder is sliding down the wall. So that's our problem situation. All right, how fast, that's a rate, is the top of the ladder sliding down the wall at that moment? How fast is the top of the ladder sliding down the wall? Well, when we talk about a rate of change, we're talking about, let's find, I'm going to put it right here, dy dt. When, at that moment, meaning when x equals 12. All this given information is applying here. Okay, so what we need here is an equation that ties all this together. We're not talking about angles here in this problem. We're talking about sides of a right triangle, so we are talking Pythagorean theorem. Okay, x is changing, y is changing, 13, the hypotenuse is not changing. So we have to put variables in before we differentiate. We don't want to differentiate too soon. We're not going to be able to find what we need if we did. So x is changing over time, y is changing, 13 is constant. Let's bring in our derivative operator. And the derivative of 13 is 0. All right, I'm finding dy dt. I'm going to choose to go ahead and plug in values here. Sometimes I like to solve for dy dt and then plug in values, but I'm going to go ahead and plug in some values. So it looks like I've got 2 times x, and x was told to us to be 12, and at that moment the rate of change of x is 5, and it's positive, plus I have the 2 from this expression, and here y, and then dy dt is what I'm solving for, and then equals 0. Okay, let me find the y component. So I'm coming back over here, and well, that didn't give me any information about y, but they did tell me the ladder is 13, and I have to consider when x is 12. Those are the values I'm plugging in. So when x is 12, just think about that we could use Pythagorean theorem to solve for the missing leg. So if the hypotenuse is 13 and x is 12, that would look like 169. I'm squaring. 169 minus 144 is 25. The square root of 25 is 5. So it appears that my vertical component is going to be 5 when x is 12 and the hypotenuse is 13. So let me come up here and do some calculations. That's 60 times 2, 120, plus 10 dy dt equals 0. Subtract 120. Divide by 10. And I ended up with negative 12. Okay, and that makes sense. The rate of change should be negative because the y component is decreasing. So if x is moving to the right, the rate of change will be positive. If y is decreasing, then the rate of change will be negative. And the units of measure would be feet per second. All right. There's some other things that we can do with regard to this ladder problem. So let's look at question B. At what rate is the area of the triangle formed by the ladder, wall, and ground changing at that moment? So at what rate, already we know what kind of notation, area of a triangle, that's the equation I'm going to be differentiating, formed by the ladder, the wall, and the ground changing. So I'm talking about the area in here. Okay. So when x is 12, what's the rate of change in the area? It probably is going to be negative. I bet the area is getting smaller because when x is 12, this ladder is near down to the ground. So that triangle is getting smaller, the area is getting less. I bet the rate of change is going to be negative. The area is decreasing. Just trying to make some sense of the problem. All right, so what are we finding? We are finding dA dt. That's a triangle. I'm going to do a 1/2 base times height. Instead of a base times height divided by 2, I'm going to think about the constant multiplier situation that I've come accustomed to. Okay, unfortunately, like the cone problem, we are not going to be able to get rid of B or H in this problem. I could have used X and Y, and I likely should have based on what I had here. So, I think I am going to go back and change this to X and this Y. That's our base and our height. And like I mentioned, as far as the cone problem is concerned, and the cone problem, we got rid of the R, or we could get rid of the H. Here with this triangle, I don't believe there's any way to get rid of one of the variables. We don't have a similar situation. We don't have two triangles going on. So we just have to jump into the product rule. Okay. So dA dt equals, and I guess I'm going to leave the 1/2 out front. So I'm going to focus my attention on that product where x is the first factor and y is the second. So the first times the derivative of the second with respect to time, x dy dt, plus the second factor y times the derivative of the first with respect to time. All right, let's just go ahead and see if we have everything we need to plug in to get a rate of change of area with respect to time when x is 12. All right, so we've got the 1/2. This is for x, this is for dy dt, and this is for y, and this parenthesis is for dx dt. See, x was 12, rate of change of y, oh, okay, we found that, that's negative 12. The y was 5. The dx dt was given to us, and that was 5. So negative 144 plus 25. Negative 144 plus 25 would be negative 119. Oh, don't start that. So my final answer would be negative 119 divided by 2, almost negative 60. Indicate units of measure. It's a change in area over time. Area for this particular figure would be measured in feet squared, square feet. The unit of time was second. So that's our rate of change of area with respect to time. We have a right triangle, so we can work with the sides of the triangle. We can certainly work with the area of the triangle. And the very last problem here that we're going to look at is something we've looked at so far too, is going to be a rate of change in the angle. So we're talking about some trig going on here in this last problem. So let's see if I can scoot this up a little. All right, right here in example C, what we're going to do is we're going to find the rate at which the angle between the ladder and the ground is changing at that same moment. So if you want to refer back up to your illustration up there, make sure you're talking about the correct angle here. Okay. Okay, so we have this right triangle. We're talking about, oh my goodness. We're talking about this angle right here, the angle between the ladder and the ground and how it's changing at that moment. So we're going to find d theta dt. And so what we have here is a horizontal component and a vertical component and a hypotenuse. The hypotenuse is not changing. So when we have to pick a trig ratio, you know, sine, cosine, and tangent would be the ones that I would want to choose from. And because I know I'm going to differentiate, I always try and use the easier one. And I'm thinking sine would be the one. Sine of theta is equal to, it's going to be the opposite over the hypotenuse. So you want to take advantage of that hypotenuse as well. That hypotenuse is constant, and anytime I can include a constant in here to work with would be a lot better for me. So I'm going to differentiate both sides of this equation. And instead of rewriting it just to save some space and some time here, I'm just going to bring in d over dt here. Okay, let's differentiate both sides, so that becomes cosine theta d theta dt. Equals, okay, I do pay attention to the fact that this is a 1/13 multiplier. So I've got 1/13 as a constant multiplier times the rate of change of y with respect to time. So that's going to be times dy dt. Okay, so at this point, I can multiply both sides of this equation, if I wanted to, by 1 over cosine. To get rid of cosine, to isolate d theta dt, I put 1 over cosine here. But you know what, cosine is not a bad thing to work with, so I think I'm just going to kind of put numbers in here on this problem and then go from there. Not too bad. Okay, we do know dy dt from an earlier part, and that was -12. Okay, the cosine at theta, you know, I don't know what happened here. Thinking about what the cosine of theta is. Well, here's theta, as ugly as it is. The cosine is going to be adjacent over hypotenuse. Well, in this case, it's 12/13, because we knew x was 12. Okay, not too bad up here. I can get through this problem without too many more obstacles. We're going to have -12/13 on the right-hand side, and what I'm going to do is I'm going to multiply by the reciprocal 13 over 12 times 13 over 12 here. So I'm going to bring in 13 over 12 here. All right. Cleaning that up, it looks like we're going to get -1. Well, what are the units of measure? -1 what? Well, we're finding a rate of change in an angle, so we either use degrees or radians. So in this case, all our calculations have been done just with numbers. So we're going to say that our rate of change is in radians, and the unit of time was, there it is, seconds. So the angle is changing at a rate of -1 radians per second. Woohoo! Got that one finished. So there's a lot that you can do with this kind of problem situation with the ladder. You can look at a right triangle. You can look at Pythagorean theorem. You can look at area. You can look at angles. So a lot for us to consider in this one little problem here. So thanks for hanging in there.